Hello, my name is Grant, and this is my artificial blood vessel. So, the main goal of this project was to test different materials and see how they would perform as if they were being used for an artificial blood vessel. The goal is to find the most viable option for this company to produce and implement on a large scale. The dimensions that we decided to test over were 1 millimeter, 10 millimeter, and 100 millimeter in length blood vessel. The inner diameter is a 3 millimeter, and a outer diameter is a 4 millimeter. I got these dimensions based off of research, which I will provide the resources at the end of this presentation. The three materials that we test across are PDMS, EPTFE, and PU. PDMS is a highly flexible silicon polymer. It is commonly used for vascular modeling and sensors, so it's already widely used in the biomedical field. So it's very easy to find backing research and data for this material. Another option that we looked at was EPTFE, mostly used for vascular grafting material. It has a high strength and large durability. Now, similar to that material, PU also is used for vascular grafts, as it has been used for many of their studies. And but it has an adjustable stiffness and it has a good fatigue resistance, which allows it to be a good balance between both PDMS and EPTFE. For the simulation setup, we use SOLIDWORKS Flow Simulation to test a total of 18 fluid sims across this entire project. That was 2 simulations per material per size. Now, the 2 simulations were one, the average flow rate of adult human male, and then 5 times that flow rate. The reason why we did 5 times that flow rate is so that we could test these blood vessels across any pressure it may encounter within the human body. This way, it has a safety factor of 5, so we don't have to worry about any issues coming up in the future. For the simulations, we tested with blood as the fluid, which was given to us through SOLIDWORKS simulations. And each simulation had identical boundaries. We had a inlet boundary, outlet boundary, and we tested to find the pressure applied to the internal surface of the parts. The absolute pressure we used was 117,325 pascals, which is equivalent to 16,000 pascals as a gauge pressure, which was that average blood pressure for an adult human male. The internal temp was 310 Kelvin, which is also that average for blood temperature. And then we also had a rigid wall assumption for the simulations. Now, as you can see, we have a table for these values of pressure and velocity for the simulations. We tested them both against 1 millimeter, 10 millimeter, and 100 millimeter, and we can compare the velocities between nominal flow rate and that 5 times flow rate. We also put in here that change in pressure for that 5 times flow rate. Now, the reason why we're focusing a little bit more on that 5 times flow rate is because it emphasizes the difference in these values, which will make it easier for us to come to a conclusion of what material will be better performing. Now, once again, we did have an absolute pressure of 117 kilopascals. And as you can see, there is a pressure change with both increase in flow rate as well as an increase in the vessel length. Now, 10 millimeter is kind of an outlier as it doesn't necessarily follow all of these trends, but for the most part, the rest of the lengths do. Now, it is important for me to note that the pressure did not change with the different materials. The only thing that affected the pressure was the length of the blood vessels, which is why we don't show the differences in each of these base materials. The materials will really only come into factor once we start calculating strain and stress. Here you can see we were also able to gather the different wall shear stress results for the different lengths. As you can see, there's the highest WSS occurring with that shortest blood vessel. The longer the vessel gets, the smoother that shear distribution gets. The wall shear stress does increase, however, against flow rate. So with that 1 times flow rate, it was a smaller value. Now, using Hooke's law, we are able to get our stress and strains for the different materials, and this is where the actual materials matter, as we need their Young's moduluses to be put into this equation, and then we can use the pressure from the previous slide to calculate our strains. Now, the hoop stress is nearly identical, and we're able to pull the material stiffnesses from this table to use for our final conclusions. Now, to explain what that table kind of showed us, we can see that PDMS had a very high strain, but it made it overly compliant, which means it was not stiff enough for this application. EPT-FE had a very low strain, which means it was too stiff for the application of blood vessels, whereas polyurethane or PU had a good moderate strain and was best compliance balanced for this use case because it wasn't overly stiff while being stiff enough to withstand the pressure being dealt with inside of the human body. Key conclusions of this project is that we know that flow behavior is independent of material and is solely based off the dimensioning of those blood vessels. The length also affects the velocities within inside the blood vessels, not the material either. Now we can see that we were able to gather the strains which are governed by the moduluses of the material, and that's where the material really takes effect is through that strain calculations. Overall, I can safely say that PU is an ideal choice and will work perfectly for artificial blood vessels. However, we only tested 3 materials across this project. So in the future, if we wanted to go further with PU, it would be best to test it against other similar materials to see how well it stands up. And these are some of the resources that were used in this presentation. Thank you.